Hello. Today I'm going to talk about two pieces of related work. In the first, we'll look at how we can use machine vision methods to detect weeds by deploying them on ground platforms, such as this robot here. In the second, we will consider a two-platform solution utilising unmanned aerial vehicles or UAVs. All methods were tested on the IBEX platform here, developed by IBEX Automation Limited for the Innovate UK funded project IBEX 2. So, automated robotic weeding of grassland will improve the productivity of dairy and sheep farms while helping to conserve their environments. Tractor-mounted bulk spraying of selected herbicides is expensive due to the volume and cost per unit of selective chemicals, as well as the environmental cost. Precision robots present an opportunity to use low and targeted doses of cheap generic herbicides at a low cost, as they can drive, detect and spray automatically without the need to pay manual sprayers by the hour. Autonomous weeding robots must first detect weeds at a suitable resolution and accuracy. Image acquisition. We constructed test plots of weeds in grass on a dairy grassland farm in South Yorkshire in the UK. Slabs of urtica or nettles approximately 0.2 metres squared were extracted from working fields and transplanted into a 3 metre squared trench. This process was repeated for rumex or dock leaves. Transplanting real slabs from areas of the working farm ensures maximum realism and avoids problems of growing the weeds artificially, which could lead to unrealistic soil backgrounds in images. The weedy turfs were watered daily for 2 weeks to allow the plants to stabilise before data collection. Plots were located in a region of the farm that is in direct sunlight throughout the day. So perspective normalisation was performed by the projective transform shown in the left figure to those in the right figure. This maps a 1.16 metre width by 1 metre depth ground area into a 700 pixel width by 600 pixel height image whose geometry is identical to that of a vertical overhead camera. However, the image is not exactly the same as that of an overhead camera due to the three-dimensional structure of the plants. In particular, tall plants at the front of the image are inflated in size because they are warped as if they were further back. The key research question asks whether this will have a detrimental effect over pure overhead imaging. Finally, images were divided into either 28 or 64 pixel squared windows corresponding to a 5 cm squared or 11 cm squared spraying resolution respectively. Next stage is feature extraction. So we either took local binary patterns, which are the middle column of images, and bin them into histograms as feature vectors for classification, or we took the absolute value of the image's Fourier transform, yielding the image's magnitude of frequency spectrum, or we performed watershed segmentation of the image. So what we did was we would segment the image using watershed, and then we would count the number of segments, and that would be one element of our feature vector for classification. Then we'd adjust a parameter of the watershed method, recount the number of segments, append the values, and we would end up with a feature vector for classification. The final feature extraction method we used was binary robust invariant scalable key points or BRISC descriptors, which were binned into feature vectors for classification using the k-means clustering algorithm. And the classifications that we used were support vector machines, linear discriminant analysis, and a simple baseline nearest neighbour classifier. Our version of nearest neighbour computes the median feature vector for weeds from the weeds training set and the median feature vector for grass from the grass training set. A test image is then classed as weeds if its feature vector minimises the sum of absolute errors between it and the median feature vector computed from weeds images. Each classifier, SVM, LDA, or nearest neighbour, can take as its input any feature type, local binary pattern, Fourier transform, watershed, BIS features into k-means, yielding 12 distinct classification methods. The hyperparameters for each method were optimised on small data sets, 10,000 training images, 1,000 test images for 28 pixel squared windows, and 2,000 training images, 200 test images for 64 pixel squared windows. Each method was then validated on corresponding training and test sets 20 times that size. Okay, the results of the study. The table below gives the results for the 12 classification methods on 64 pixel squared windows with mixed weather, sunny and overcast, and mixed weed type, Urtica and Rumex images. The column ACC, which stands for accuracy, shows the overall accuracy of each method. Confidence intervals are also reported, which justify the significance of the accuracy percentages to 2 decimal places. Breakdown accuracy for grass and weed image presentations were also given here, and those indicate the rates of false positives and false negatives. And then we have our optimal parameters for each method here. So you can see that the local binary pattern into support vector machine method performed better than the other classification methods with an accuracy of 82.88%. The best meta classifier, which combines the predictions from the 12 methods in various ways, gives small improvements here, 83.4% versus 82.88%. The best performing feature classifier combination, the LBP into SVM method, is here run again on mixed weed and weather separated as a function of the distance of the window from the robot camera's ground location for both window sizes. Classification performance decreased smoothly as the distance increased by around 15% absolute for 64 pixel squared windows and 10% absolute for 28 pixel squared windows. Weeds closest to the cameras were predicted with an 87.85% accuracy for 64 pixel squared windows, which is more in line with the high accuracies reported by the previous studies than with accuracies at far distances. However, it should be emphasised that this result was obtained for a mixture of Rumix and Urtica under a mixture of weather conditions, unlike those studies. Okay, conclusions. All the accuracies in our independent re-implementations are lower than those reported in the papers which originally proposed them. This may be due to several factors, some of which are given here. Previous work has used vertical downward pointing cameras, giving clear and equal views of each point on the ground by removing the need for perspective correction. Our data is more challenging, requiring additional invariance of perspective distance due to the requirement to operate with cameras mounted on top of robot bodies rather than protruding from them. Evidence for the contribution of perspective effects to reducing accuracy is given by the distance experiment result, which suggests that for robots that are not able to mount vertical overhead cameras, it may be preferable to concentrate visual processing power only on nearby regions of ground space. We've had our abstract accepted by the 14th International Conference on Precision Agriculture, and we hope to get it published. It is titled Rumix and Urtica Detection in Grassland by UAV. So, the previous study initially assumed that weed detection and spraying would be performed by the same ground robot, swathing, i.e. driving up and down in a lawnmower stripes pattern over each square metre of a field, detecting and spraying any weeds found there. There were two issues with that, however. First, swathing with a ground platform is inefficient because weeds are not evenly distributed in most fields. Driving over every square metre is a waste of time and, more importantly for unmanned systems, energy. Second, the previous study discovered a strong drop-off in recognition performance as a function of the distance from the ground robot due to its perspective warping assumptions breaking down with distance. Mounting the robot's cameras facing vertically downwards instead of its current 22.5 degrees would preclude it from detecting weeds not directly under it, which in turn would preclude the fusion of multiple observations of weeds ahead of the vehicle before spraying, which was shown to be needed to obtain the higher 95% accuracies. Both of these issues could be addressed by a two-platform system, using unmanned aerial vehicles to perform detection and the ground platform to relocate the detections and perform spraying. At the moment, EU law prohibits spraying from UAVs directly. Views from UAVs are different from ground platforms, and it's not obvious whether systems developed for ground use are reusable from the air. The present study tests this hypothesis and measures the effect of altitude to give the first indication of whether aerial swathing is required or whether single high altitude images can be used. It also reports classification performance as a function of the speed of the UAV. So, data acquisition. The previously trained classification method, LBP into SVM, performed for the ground robot, was used to classify test images acquired from cameras mounted to a UAV. Images of grass, Rumix and Urtica were captured from 4K resolution auto-stabilized cameras mounted on the DJI Phantom 4 UAV in May 2017, on the same field from which the ground robot images were acquired. The UAV captured images at a vertical distance of 1 meter above the ground contents. Grass and weed image test sets for any given experiment each contain 1,710 image windows. Weed image test sets contained an equal mixture of Rumix and Urtica. So we did 3 different experiments. So firstly, we wish to assess classification performance as a function of the speed of the UAV. However, the UAV test data was not acquired with the intention of obtaining speed results, thus there were no subsets of the data acquired at predetermined speeds. In order to obtain these subsets, we computed the dense optical flow occurring between 2 consecutive images using a method based on the Gunnar-Farnbach algorithm. We also wish to assess classification performance as a function of the simulated altitude of the UAV. As the UAV increases in altitude, its cameras cover a larger area of ground. At the same time, a given area of ground is represented at a correspondingly smaller resolution. Thus, simulating images taken by the UAV at different altitudes can be achieved by downsampling its 4K images to different resolutions. And the results. The left figure gives the accuracy of the classification method as a function of the speed of the UAV in intervals spanning 0.07 meters a second. The diamond-shaped markers are the data points, and the curved line is the best fitting mirrored cumulative Gaussian. The accuracy of the classification method decreases sharply beyond speeds of 0.3 meters a second. The right figure gives the accuracy of the classification method as a function of the simulated altitude of the UAV increasing in powers of 2. The square markers are the data points, and the curved line is again the best fitting cumulative Gaussian. The accuracy of the classification methods decreases beyond altitudes of 8 feet. Note that the SVM into LBP method trained on the ground robot images is performing better on the UAV test data, 87.89%, than on the ground robot test data, 82.88%. Okay, conclusions. The results show that simple reuse of the existing ground platform algorithm does perform sufficiently accurately on UAV imagery to make hybrid UAV detection and ground spraying weed control possible and economical. The system performs well at low altitudes, up to around 8 feet, then quickly falls off with higher altitude. This in turn suggests that to fully check whole fields for weeds, UAVs must perform some swathing rather than work from single high altitude images. Such swathing could be automated, requiring more effort than taking a single manual high altitude image, but would operate much more quickly and use less energy than swathing with heavy ground platforms, so is worth further investigation. Okay, I'd like to say thank you for listening. Sorry I couldn't be there in person, but if you have any questions, please send them to this email address here at the bottom, adambinch@gmail.com. Once again, thank you for listening. Bye.